I collated some notes and 2 buffer overflow examples in a GitHub repo, which I'll share in the video description. So this is a typical OSCP-level buffer overflow, and you'll require a 32-bit operating system, either Windows 7 or 10, Immunity Debugger, which is an old-school Windows application debugger for 32-bit applications, the last released version of Python 2.7, and Mona, which is a plugin for Immunity Debugger. When you install this, install Python first, because otherwise Immunity's installer will try to install its own version of Python. And then read the instructions on the Mona repo for installing Mona. If you have access to the Pen 200 lab or getting ready for the exam, do note that you will get development machines where all of these things are already installed for you and configured correctly, so you can just use it. We'll be looking at the SyncBreeze application. This is a well-known vulnerable application to buffer overflow, so you might have seen it in other OSCP preparation material or recommended challenges. You can get the vulnerable version from exploit.db. So under vulnerable app, there's a link. You can just download the installer right here. Don't look at the solution. We're going to do that right now. In the SyncBreeze folder on the GitHub repo, there's a solution folder. Don't look at that unless you really need to. And there's a POC script. So this POC script is just going to crash the application in a way that demonstrates the buffer overflow, and we'll need to work from there to build a fully working exploit. So I cloned the repo locally, and I'll be using Visual Studio Code to write my exploit. This is what the POC script looks like, and we'll be working in this area where we build this malicious buffer. If you look at how that's used, you can see it's targeting a system on port 80 and just sending a post request. So this post request contains a body with a username and password, and the buffer overflow is in the username field. So we're not going to be fuzzing and discovering the exploit point. We're just going to be going from this point onwards to build our exploit. So we're sending 1024 A's to show that there is a buffer overflow vulnerability. And you might ask, well, why 1024? So you could send 1,000, which is enough to cause this application to crash. But typically you would try different sizes. So maybe begin with 500 or 200 even, and then go up to like 4,000 or maybe 8,000 or 20,000 even. Just send different sizes of buffer, and you don't want to go too large, because if you send a buffer that's too big, the application might actually reject it before it overwrites the buffer. So it might see, okay, this person sent too much data, and there might be a check in the code. Or you could override too much of the stack and actually hit the exception handler and cause a different error. For example, in the free float FTP application, if you send 1024 characters, it's going to break in a way that you can't exploit. So just be aware of that. You need to just try different sizes. I usually begin with 1024, just because it's a multiple of, or a power of 2. But you could do 1,000 or whatever. This is my Windows virtual machine. It's a Windows 10 32-bit instance, and you can see I've already got SyncBreeze Enterprise running. When you install it, you want to run the SyncBreeze client. go to Options, Server, and make sure you check Enable Web Server on port 80, which is disabled by default. So from my Kali machine, I can browse to that server and see that it's indeed accessible on port 80. If yours isn't, just check your firewall, disable firewalls, and make sure you can access that application. So next, I'm going to run Immunity Debugger as administrator. Since this application is running as a system service, you need to run as administrator to attach to it. You could run applications that are running as your user. You don't need to run Immunity as administrator, but I recommend just running it as admin anyway. Then you won't have any trouble. Since this is a service application, you can't just open it in Immunity and run it from Immunity. You can do that with the free float FTP application, but for a Windows service application, you typically need to attach to an already running instance. So that's what we'll do now. Just click attach and then type the word sync, and it will filter to sync BRS. That's the process we're targeting. Attach to it, and you'll see what these debuggers do is they inject a bunch of int3 codes. So that is an opcode to actually cause a debug breakpoint. And in the bottom right hand corner, you'll see that it's currently paused. So if we just hit play, it's going to resume execution. So bottom right hand corner now says running. So it's being debugged, and if we now send this malicious buffer, it should cause that application to crash. So I'll just run Python 3, this POC script, and the target IP address. Sending payload sent. You can see right hand bottom corner, it's saying it's now paused. Left hand corner, it's saying access violation when executing 41414141, and 41 is just the hexadecimal representation of a capital A. So that's what that means, and it indicates that we actually have control over the execution, and specifically the instruction pointer. So this instruction pointer points to the code that should be executed next. But we just filled it up with a bunch of A's, so that's invalid and the application crashed. Another interesting thing is that ESP, which is the stack pointer, points to an address that is filled with a bunch of A's. So that also means we can control the contents of ESP, and we have control over EIP, the instruction pointer. So what we want to do is basically figure out how many A's do we need to send. So how many A's before we control EIP, the instruction pointer, and then replace EIP with a valid address to, let's say, address to something like jump ESP. So this is typically how these challenges work, is we need to run shellcode that we put in ESP. And we can't just hard code the address of the stack area where our shellcode is, because it's typically a random address because of not full address space layout randomization, but something similar where in a multi-threaded application at least, and I think in all modern operating systems, we'll just randomize where the threads stack is. So you can't just hard code where your shellcode is. But since we know we've got control over ESP, so wherever this is, we can just tell the instruction pointer to jump to that address, and if our shellcode is there, it should execute. So we'll replace EIP with jump ESP or something similar to just go to the shellcode on ESP, and then we'll put shellcode in the stack. So put shellcode in ESP location. So that's typically how these challenges work, and we'll be working through those steps now. So firstly, how many A's do we need? Now it's difficult to count A's, so we'll use something called a pattern. So there's a utility called MSF pattern create. So I'll just use that. And it's got a sibling utility called pattern offset to, once you know what the pattern value is that ended up in EIP and in ESP, we can use offset to actually locate the address. So I'll just use it with tag H for help. And it says we can use it with tag L and a length value. So I'll just use 1024 because we know that worked before. So instead of 1024 A's, I'm just going to paste this whole string in there. And then on the target, we need to restart immunity, restart the service. I saw for some reason, if I don't fully restart immunity, it doesn't work. It might just be my machine. But that's why I'm not just restarting and reattaching. So it's running again, and I'll just run it against this target again. Okay, so this time we see EIP has got this weird value in there, so that's part of our pattern. So I'll just copy that numeric value just like that. And then I'll run pattern offset, just with the help again. And it says you can run it with tag Q for query. And I'll just paste this numeric value we got directly from EIP. And it says the offset is at 780. So I'll just create a global static value for that. Offset equals 780. The other one we want to know is where, like, what is the index of this string, because we want to put our shellcode in there. It's like you can't just easily copy it in immunity, so I'm just going to remember 4 characters, so 2 capital B A3 and 2 capital B A3, same thing, pattern offset. So it says this, the contents of the stack is at 788, so I'll just add a comment for that. We'll use that later. So next, now that we have the offsets, we want to just fill this, before we hit EIP, we want to get some junk characters in there, so just A's as we used to have. And then after the 780 A's, I'm going to put in just 4 B's just to check, because this should be going into EIP. So this should overwrite EIP, so we can validate that. And I'll just comment this to say this is junk to get to EIP location. And then after EIP, we'll just add some more junk to get to ESP. Because EIP starts at 780 and it goes to 783, because it's 0, 1, 2, 3. And then this next few characters goes from 784 to 787. And we know that ESP's contents actually starts at 788. So this should be going into, should be ESP's contents. So we can just validate that. We can send this to the server. Just need to restart it again. And we can see this should be ESP's contents in ESP, so that's great. And EIP is now 42424242, which is B's. So everything is working as expected. Restarting this along. Okay, so next we want to identify bad characters. Now, bad characters are byte values that if you send them to the target application, they don't come through as expected. And you can think of this sort of intuitively. So what if we, in this buffer, that's going to be the value of a post parameter, put the character ampersand. So in the string, it's going to terminate the value that goes into username, because then it's a different like the next parameter. That's how it gets terminated. Or what if there's a new line? So if it's going to the next line, or if there is, say, a space in there, then it might also break it. So things like that are like just the way to intuitively understand this, but we'll do it in a way that we can be certain we know exactly which characters aren't allowed, because we want to generate shellcode and make sure none of those bad characters are in the shellcode. So I like to do it this way. I like to say generate bytes from a list so that I can use sequences in Python. So I say b in range 256. Actually, b4 b in range 256 if b not in bad chars. So this is just something you need to remember exactly. You can put this in in your notes. And bad chars is just another constant value that I'll define up here. Currently it's an empty list, but we can add values in here like as we go, we can add characters in there and see which ones are bad characters by sending it to the server. I'll just show this just to make it very clear. So if we say bytes for b for b in range 256. I'm not going to do the if not in bad characters right now, but you can see this is what it generates. So it's just all the byte values from 0, 1, 2, 3, or some of them are valid numeric and alphabetic and printable characters, so those get shown. Otherwise, it's just basically all the bytes from 00 to FF. So I'll send that to the server, and we can have a look at what came through. So what you want to do is click on the address of ESP and then say follow in dump. And we can see the first value after our A's and B's and C's is 0. So that's the null byte. So the null byte came through, but then we're expecting a 1 and a 2 and a 3 and 4. So the fact that those didn't come through probably means that the null byte actually caused string termination, because the null byte is used in C to terminate strings. So I'll add the null byte in there as a likely bad character, and we'll just run this again. I did something wrong, so I'll just restart this and try that again. Okay, right click on ESP, follow in dump. Now I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's a null byte which is wrong. It should be 0A or hex 10. So I'm thinking 0A is a bad character, and it often is, because 0A is the new line character. Let's restart this again. And we've added the 0A, so we'll send it again. Same procedure, follow. So now it goes to 0C, and then there's a null again. And 0D is a bad character. And that's also a very common bad character, because it's actually part of the new line in Windows, because Windows new lines are 2 characters. One is new line and the other one is carry out return. So it's running again, saved, send it again, follow in dump. Okay, this looks better. We're going up to 24 now, so 25, another bad character. And it went up to 24 again. We didn't send 25, so this might mean that 26 is a bad character, or it could mean that 24 actually came through, but it broke the rest. So it might be that 24 is a bad character. I'm just going to guess 26 is also a bad character, and then if that doesn't work, I'll try 24. So 26, send it again. Okay, so now we're up to 3C. So I'm guessing 26 was the bad character. Something you need to be aware of is not all bad characters break the rest, but some of them actually change their values. And in this case, you can see there's a 20, 21, 22, up to 29, and then 2A, and then we're expecting a 2B, and then 2C, but 2B turned into 20. And this is actually interesting because it's a post parameter, and 2B is the plus character, and 20 is a space. So when a plus character gets URL decoded, it turns into a 20. So I didn't break it, so we need to add 2B as a bad character. And then it went up to 3C, so 3D, I guess, is also a bad character. So 2B and 3D. Okay, so this looks better. It's going from 1 to FF. So everything came through. We just need to make sure that there aren't any replacements. An easy way to check this is if you have a lot of continuous characters, you can see, like check it per column. So you can do E6, 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 E6. And you can just sort of eyeball it quite quickly. But you need to make sure you don't miss anything, because if you do, then your shellcode might not work and you might not know why not. Or C, B3, 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 2A, 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 F9, 19, 19, 19, 19, 80, 80, 80, and then F7s all the way. So this looks good. It looks like we do have all of the bad characters now. So at this point we can replace this with actual shellcode, and we still need to get a valid address for a jump ESP or something similar. But let's do the shellcode first. So I'll use Metasploit to actually generate it. MSF Venom. I'll just get my IP address, so it's on my Ethernet. But in the exam, it will probably be on your TUN0 interface. I want to use Windows reverse, no, shell reverse TCP. So if you are generating a 32-bit shellcode, this is how you do it. If you do 64-bit, you need to specify 64-bit. But if you don't, it's going to be 32-bit. This is an unstaged shellcode, so if you want to do staged, you add a slash there. But the nice thing about unstaged is you can use Netcat to handle it, so you don't need to use something fancy like Metasploit's handler. You can use this. I think in the exam they will tell you which payload you have to use for the exam, so just keep an eye out for that. So my attacking host IP is that, and I'll listen on port 9000. We need to specify the bad characters, so we've identified these bad characters. Just copy it with the quote. We want to output format Python, and I like to specify my variable name as well, so I like to use shellcode as the actual variable. So you can see there's my variable name, shellcode equals all of that. So this is my shellcode, and it is 351 bytes. And I'll just paste this up here somewhere. So during the bad character analysis, we know that, well, about 250 characters came through fine. But we didn't actually check that it's going to be good for 351. So we could, if you wanted to, also do something like this. We say we want to send 400 Ds, followed by maybe just like 4 Es, because we don't want to just send the Ds because it's going to be difficult to count 400. But if we see this send through fine, and we see some E's at the end, we know, well, at least 400 D's came through. So then we know we do have enough space. But I think I'm going to skip that in this case. We're just going to assume that we do have enough space caused by the buffer overflow. And that's just because sometimes you don't get infinite amount of space. You only get a certain amount of space, and you need to be cognizant of that. So there's our shellcode. and we need to be able to jump to that. So in EIP, we want to get a valid opcode, or the address of a valid opcode that's going to jump to ESP. And the way we find this is using mona. We say !mona. We want to jump to the register ESP, and we want to avoid these bad characters. I thought I still had that copied, but not. So I want to copy that, including the quotes. Just like that. So it's going to avoid addresses that have those bad characters in them. So I'll run that. You'll see my screen flashed a bit, but I need to go to the log data output to actually see the results. So these are the 8 addresses it found. You'll see there's one that does a clean jump ESP, so that's going to be a definite winner. All of these addresses are in a DLL called libspp.dll, so it's not in the exe itself, which is interesting. So a 32-bit application, the exe itself is typically in a lower address where it's going to start with a null byte, which is a bad character, so it's typically unusable. And you'll usually see that the good gadgets like these, and it's called a gadget because you can use this address and it's going to do it's going, like when you jump there, it's going to do a certain function. So you can in binary exploitation, it's just typically called a gadget. So we can use that one, it's going to work fine. I'm just going to pick another one just to show that they also work. When you look at these, you'll see there's a push ESP, so it's going to put the address of ESP into the stack, and then it's going to do a ret, which is popping the address of from the top of the stack, which is going to be ESP, into your instruction pointer. So that's going to work fine too. You'll see there's a ret 4 and a ret 8 as well. So these do the same, except they also, after it actually does the return, it's going to skip over a single address or 2 addresses on the stack as well. So you'll just need to add more buffer if you use one of those. I'm just going to use this one, and I'll just say copy to clipboard the whole line. And then instead of the B's, we're going to jump to that address. Or actually just put that address into EIP. And you can't just do it like this. You can either manually write it, so it's little endian, so you need to do it in reverse. It would be 27, so from the back, 27, 8C, 13, 10. But I don't like doing that. I like to use a function called pack. Just import it first from struct import pack. So pack will just do that automatically. You need to specify in what format you want it. So less than character for little endian and capital I for a 4-byte value. So we don't want it in big endian, and we don't want it in a different number of bytes. I'll just show that as well in Python. So from struct import pack, and I'll just copy this over. And you can see it's the same as what I did before. You can't see the 27 because it's a valid or a printable character. I'll just do it in X. So 27, 8C, 1310. if we did it big endian, it's going to be exactly the same as it was over there. This is just the bytes representation of the same thing. And if you do different sizes, it's going to, I think this is a 64-bit, this is what you would use in 64-bit. But we just want that, so that's why we're using little endian and I. So that should work fine. But something to note is we're going to be returning to the shellcode, and the shellcode is encoded by Metasploit or MSF Venom using this Shikata Ganai encoder. So when this shellcode begins executing, it's going to try and decode itself, but it actually uses some space on the stack to do that decoding. And since our shellcode is exactly in the beginning of ESP, it's actually going to break itself while trying to decode itself because it's in the same position. So to avoid that, we want to add some buffer. And the only way you can add buffer, because it needs to be executable and it needs to be buffer, is using something called nops, which is, so this is shellcode, but it's going to do no operation. So it's called a nop to create buffer on ESP. So it's going to run over those, but ESP is still going to point to that address. And I want to do 16 of those. So you want to do multiples of 4 to keep the stack aligned. And 16 is enough. So 16 is basically 4 addresses of nops. Just something you could do as well is maybe add a breakpoint, like a hardware breakpoint. So we saw earlier you can do CC, which is int3. I showed that in Immunity when the debugger attaches, it actually, the debugger itself actually injects some debug breakpoints. And this is just useful to see what's happening. So if you are in the exam or busy with the challenge, you could do one of these just to create yourself a breakpoint and make the debugger stop. But you need to be careful to take this out before you do it against the live target, because otherwise it's going to stop execution instead of actually running your shellcode. I'll just show this. So it is running. It is still running, and I will just send this to the target. And here you can see those are the nops we sent through. So it actually just ran through them. And here's my int3 debug breakpoint. And it actually paused right after executing that. At this point, I want to start my Netcat listener on port 9000. And then just hit continue. And hopefully I get a shell, and there we go. So who am I? System. When I run this against the live version of SyncBreeze, no Immunity debugger involved, and we need to remember to actually take out this int3, so we can either make that 16 or just change this to that. What I typically do if I have more time, I would say if debug, and then I would say have a debug global variable, and say then insert the int3, otherwise just do a regular nop. In this case, I just want to have a very clean code base. And this should be our whole exploit. Make sure Netcat is listening. and the application is running, no immunity involved. Send it through and we get a shell. For the exam, I really recommend you practice about 10 of these, so different challenges. They all follow the same workflow, but there might be slight variations, and you need to get very comfortable. So you need to be able to do this in your sleep and also know what to do if things go wrong, because the last thing you want to do during your exam is get flustered and don't know what to do. The buffer overflow challenge, if you get it, should take you no longer than 1 hour if you've practiced this and built up the process in a way that you really understand each part.